providing some important context for today. So I see we've got 78 users on the Zoom. I see we have a similar number of people logged in on the Jupyter Hub. Please let us know in the chat if you're having any problems logging into the Jupyter Hub, or if by any chance maybe you forgot your password from yesterday, we can reset it for you. No problem. Unless there's any questions or concerns to hit at this point, I'm going to go right into a brief overview with some slides on PyCalphad, and then we're going to get right into the interactive session. So I'll pause for just a moment, just in case there's anything pressing. Seeing none, we'll just get right into the next part here. Is this coming through okay? Are we getting the full screen?
Yep, looks good.
Looks very good.
Great, thank you. Just double checking with this. Okay, so I am Richard Otis. I am a director at the Materials Genome Foundation. I'm also the creator and lead developer of PyCalphad. So I'm very excited to be here today and share PyCalphad with you, and also share some of the work that the foundation is doing in reproducible interactive computing with services like MGF Cloud, which we're sharing with you here publicly for the first time. So we're very excited about this. So you've already got a little bit of an overview of Calphad and a little bit about PyCalphad, but PyCalphad is an implementation of the Calphad method. PyCalphad has been around now since 2014. The Calphad method itself, of course, is a good bit older, as you just learned. The major thing that PyCalphad lets you do is compute anything that can be connected to a chemical or thermodynamic process. And it also helps enable the designing of new thermodynamic models that can contain new physics. So actually custom property models, and we'll learn a little bit more about that today during the interactive session. The other important thing to know about it is that it is free and open source with our website, which is at pycalphad.org, which has all sorts of information, installation instructions, and documentation. So some reasons why you might be interested in using PyCalphad compared to other options that might be available to you are the ability to develop custom Gibbs energy models. So including or prototyping new types of physics for the free energy. This modular architecture for the system that's developed by PyCalphad really enables you to do this. Custom material property models. So these are models not specifically for the Gibbs energy, but for any other material property as a function of temperature and composition that you can write down a formula for. It's possible to implement in PyCalphad. And we'll do that today. We'll show how it's actually possible to implement a Calphad-based thermodynamic model for the viscosity of a liquid using PyCalphad. Another important reason is because of the design of PyCalphad, it's really native to the digital notebook, the Jupyter Notebook environment. And so it's very easy to run from an interactive notebook environment, as you'll see today. The other thing is because of the permissive licensing for PyCalphad, it's very easy to deploy it to a cloud-based system or an HPC system or institutional computing resources that you may have at your organization. It very naturally lends itself to being able to be installed in those environments. We package PyCalphad to make it easy to install in as many places as possible. Another important reason you might want to use PyCalphad is an indirect one, which is for semi-automated database development via the SBay software package. So PyCalphad is the computational kernel of SBay. And so if you're an SBay user, you are also a PyCalphad user. And you'll learn more about SBAY today when Brandon will begin the session on that. So some notable recent features that we have in the PyCalphad 0.8 series. So we're up to 0.8.4 these days. But in this series, we did a lot of work to protect the modular nature of PyCalphad, but really reduce some of the just-in-time compiler startup time. So now we've got that down to nearly 0 for simple systems. We allow you as a user to specify your own reference states. We'll do an example about that today if we have time. Binary and ternary phase diagram plotting. You can do chemical potential conditions along with temperature, pressure, and composition. Step and map calculation, global minimization. So that gives you your automatic miscibility gap detection. We support that natively. We also support the associate model and the 2 sublattice ionic liquid model. All of the accepted, I would say, models for magnetic ordering. So that's the Enden-Hillert-Yarrow model, as well as the model from Wei-Shang. We support, as well as many of the other models you could potentially want to use, like the order disorder model, 2-state model, Einstein model. And we are supported on Windows, Mac, and Linux platforms. So in terms of limitations, I'll say a little bit about limitations you could run into. So we are currently working on improving the solver to allow for more advanced types of conditions, like being able to set the amount of a phase. So this is really useful for doing things like direct computation of transition temperatures, particularly for multi-component systems. We are working this, and we hope to have something to share early next year. We also currently have in progress some work. So this work's primarily going on at Penn State, developing an implementation in PyCalphad for the modified quasi-chemical model. We're really excited about that. There's a lot of really interesting CalPhad applications for the quasi-chemical model. And we hope in our next major version to provide a first implementation of that. And then there are also a couple of TDB files, so the CalPhad database features that you might find in, say, a database from in the literature that works with thermocalc. There's a couple of options that are not, I wouldn't say they're common, but they're not uncommon that you could potentially run into. But if you do end up getting one of these error messages, you just reach out to us. We can usually help you work around the issue. So I did also want to highlight a couple of use cases. So PyCalphad's been around long enough that we have started to collect use cases from the community. So the way we defined these was no one from the PyCalphad development team was a co-author on the paper. So we actually found out about this work the same time the rest of the community did, which was exciting. So these were people that were able to largely independently do this work, and PyCalphad was a component of it. So one of which was some work in a model for 2-phase elastic constants. So this is primarily based around nickel, which is really cool. And we also had some work, different authors, but I believe it was the same group, on interfacial energy. So actually building CalPhad-based models for the interfacial energy. And then recently this year, there was also some work using machine learning with PyCalphad. So PyCalphad itself is not a machine learning package, but what they did was they used PyCalphad to collect the training data. So they collected a representative amount of TDB files from the literature, and then they computed all of the phase boundaries that they needed that was relevant for their analysis. They extracted all those phase boundaries in a high throughput fashion, and then fed that in for their machine learning analysis. And so you can go and take a look at their paper on arXiv. But I thought that was a great use case of PyCalphad. What all of these use cases have in common is that it would have been difficult or impossible to do the analysis or do this work the way that they did it with any other tool besides PyCalphad. And so you can feel free to reach out to me at richard.otis@materialsgenomefoundation.org. Our website's pycalphad.org. And we also have interactive chat on Gitter. which you can reach out to us, and we often will field support questions through that interface. And I should say, all participants, you have a copy of the slide deck I just showed you is in your workshop folder along with all of the exercises. So I'll pause for a moment before we get into the interactive session in case we have any questions, and I'm happy to field those now.
Hi, Richard. This is Aurélien. Do you hear me?
Yes. Hello, Aurélien. Glad you can make it.
Yes. Yeah. Thank you. Thank you for the introduction. I just have a quick question about the option B or F that you were talking about for like the forcible lattice model. So does it mean that we have to technically rewrite and enter manually the equivalent technically n members due to the symmetry?
Yeah.
Okay.
Yes. So what option B, we'll get mildly into the weeds of this for just a moment. So option B and option F are ways of only having to specify the just the bare minimum of the interaction parameters in the like the 4 sublattice FCC or BCC models. Currently, PyCalphad doesn't yet support those options. So what you have to do is you have to enumerate all of the interactions and specify them manually. And you can actually write a Python script to do it, and we can help you with that if that's an issue. We will eventually implement the options, but at the moment we're just using this workaround.
Thanks.
Yeah. And so I also saw a question in chat. So Sergey, I think you're asking about the solid oxide model, so the charged species, and which I assume you're talking about charged species for solids. And we very nearly support it. And what I think is going to happen is when we release the new solver, which will have support for new advanced conditions, I'm expecting that we will almost get the solid ionics models for free due to, there's some technical reasons why that's the case, but basically all the machinery is there for it to work today. And we just need the new and improved solver to use that machinery. So I hope that early 2021, we will have a public release available, which will support that. That's currently the plan. I also see another question asking about if we have an optimizer to do thermodynamic modeling. So SBay is that thermodynamic optimizer. So some packages ship their CalPhad calculation engine and their optimizer together as one package. For PyCalphad, PyCalphad and SBay are designed to be used together. So if you do thermodynamic modeling and doing the thermodynamic optimization of the parameters, then you would install SBay as well. If you only are interested in using currently existing databases, then you don't have to install SBay. You just use PyCalphad.
Richard.
So I see we also have some other questions asking about the details of the quasi-chemical model implementation. And so Ed, I can send you, it's the MQM, it's the papers from the FactSage team that have been published over the years, kind of their 4-part papers. I can send you a link. We have a write-up about what we've done so far on this. But I know that this is a special area of interest for you, and I will tell you that one of the things that's possible to do with PyCalphad, if you're doing new advanced models for short-range ordering, it's actually possible to write those in PyCalphad and test out new ideas today. Yes.
Richard?
We have any other? Yes, go ahead, Seti.
I have a short comment about the Zikwe's slides. With the thermodynamic modeling optimizers, FactSage actually has an optimizer as well. and it is completely Windows version. It's not like you don't need to console mode or commands or something like that. So that's one thing. And the other thing is that I think, correct me if I'm wrong, OpenCalphad also has an optimizer.
Yeah, that's correct.
So okay. Well, so that is the answer. Yes. So there are other thermodynamic optimizers available, and I hope that you will be convinced over the course of the workshop today about why SBay has certain features which we think put it a little bit above.
That I'm completely sure about. Yeah, that I don't have.
Okay.
It's just because I was not completely sure about some of those things. I just thought maybe I can bring it up because it's just like to inform others that are in the workshop. That's all.
Sure.
Yeah.
Thank you, Seti. And so I will answer this one last question I see in chat, and then we have to move on. Asking about if it's possible to import and use other databases like commercial ones. So if the TDB file is available in the open as an unencrypted TDB file, then PyCalphad can probably read it. If it's a commercial database, then PyCalphad probably cannot read it. So due to restrictions. So, but we will, in addition to that, we will also show you today how it's possible to use SBay to create your own thermodynamic databases as well. All right, so we will move on now to the interactive portion. Okay, so the screen should be coming through now. You should be seeing my Jupyter Lab screen on MGF Cloud. So the way I navigated here was I clicked the workshop folder, and you should now see a PyCalphad subfolder. And I have opened this 01 plot activity notebook. And so the way we're going to do this today is we're just going to go through these notebooks in order for this portion of the session. And so for this part, what we did was we have a lot of text in here. We tried to design these examples to be a little bit self-documenting, just in case you're not able to keep up and do all the typing and everything. But I will try to go slow enough that for the people that are interested in going a little bit further in depth, we do have time and we do show a little bit about that. So first, when we introduce this, is we have to say a little bit about databases. You've already heard a lot about databases so far today, but any calculation in PyCalphad or any Calphad-based tool requires you to define a couple of things. The first is a database. So that database contains the thermodynamic model parameters, which have been optimized for you to represent, experimental data along with atomistic data, any data that was available to capture the thermodynamics of the system. Then you have to define the components that you want to consider in the system. So this could be pure elements. This could be, tightly bound species like H2O, for example. Could be an independent component. As long as it's a thermodynamically independent component, it could be considered in the calculation. You have to pick which phases you want to consider, and also then the conditions of the calculation. So this, for example, would be like the temperature, the pressure, the composition, total size of the system. And so these Calphad database files are made largely by researchers who model the individual Gibbs energy of the phases. And these parameters, once they're optimized and modeled, they're stored in databases. And one of the most common, so TDB is not the only database format that's used in the Calphad community, but I would say that it's the most common. They're usually saved with an extension of .tdb. And so we can read these in PyCalphad by running this code that we have listed here, where the first line from PyCalphad import database. So that's the import line to load the database class. And then the second line, db equals database, and then we pass a path to the TDB file that will create a database object that we can then use for further computations. Now, one of the most common questions that we get asked is, okay, so I have PyCalphad, where do I get TDB files to do calculations? And so this can be challenging. This is a challenging question in general. There are a few resources that you're able to use. I would say one of the great places to start, if you're just trying to get a sense of what's out there and what's available, is the TDB-DB. So this is a service that's provided by Professor Axel van de Waal at Brown University, and you can use the TDB-DB to search for what's available in the literature. So, like for example, I could put in iron aluminum, and it provides an indexed list of TDB files that are available from various literature sources, and you can go in and read the paper. Now, I do feel I have to warn you, as a CalPhad practitioner, these databases, they have components in them that doesn't necessarily guarantee anything to you at all about the accuracy of any computations that you might do. What I typically recommend to people is that a service like the TDB-DB is a starting point to discover what's available, and the onus is still kind of on you. I mean, it is on you to verify that a calculation is suitable for whatever purpose that you're trying to do. But in my experience, it is a pretty good place to start. So for the examples today, we have already done a little bit of legwork in finding some suitable databases for the purposes of doing these examples. Though again, I do want to give the disclaimer that you'll be able to take all of your workshop material home with you after this today, including these databases. But just be aware that we're not providing you any kind of warranty about them, about whether if you do different calculations that you will get any kind of you understand. Moving on. So the first thing that we're going to do today with this exercise is to calculate and plot the activity of a component in the liquid phase. So this is kind of a basic calculation that starts to get you a little bit of the flavor of how PyCalphad works. So what we're going to do is we're going to actually compare the CalPhad-based computation with some experimental results from elsewhere in the literature. So we have some experimental activity data here. So this is a composition of zinc versus activity. So this is just some data that was digitized from a paper in the literature. So this is some data that was digitized from the literature. It's pure zinc at this temperature of 1073 Kelvin. And so the first thing that we're going to do is we have to set up the calculation for aluminum zinc. And so we have a database here which we took from May. And okay. Give me 1 second. The dog is a little bit excited. Thank you all for your patience so far. Sorry about that. So the first thing you have to do is you have to set up the database. And so we've got the first line we have up here. It's similar to the line that you saw earlier. So this is an import line. So first we have to import PyCalphad. What we do from PyCalphad, we import the database class. we also import this object called equilibrium. And then we import another object called variables. So this has all of our temperature and pressure variables, but we don't want to have to write out variables the whole time. And so we'll do this, abbreviation where we write variables as V. And so then we can refer to the variables object just as V. The second line, we also, because we're going to need it later, we also import NumPy. And we do a similar abbreviation trick where we don't want to write NumPy the whole time, but we'll actually just write NP. And so then we also have our database, and then we define the components, the phases, and the temperature. So we're just going to run everything up to this point so far. So I'll take just a moment to read in the database, and then we'll continue on. So, all activities you have to specify relative to a reference state. So we're going to calculate our reference state at the same time. And then we're going to be able to subtract away the reference state to actually compute the activity. And so this is our first encounter with the equilibrium command. So the equilibrium command has a couple of arguments here. We have the database, the components, the phases, and then the conditions. And if we ever get lost or forget about what actually is possible to specify, we can do the same trick that we learned yesterday, where we hit Shift plus Tab, and it brings up a little bit of information about how to specify all of the different commands and options. And there are quite a few number of options. And this is also documented on the PyCalphad website. But what we're showing here is actually the most common way to specify it. And so we have our database, compositions, phases, and then we specify the pressure, temperature, and then the mole fraction of zinc, which we just set to 1 because we care about pure zinc. You'll notice we're actually short a condition here. We didn't write that n equals 1. That's implicit in PyCalphad currently, though you can just specify it directly. So we're going to run, perform that calculation. We get a warning. That warning is a bug. We can ignore it. The next thing we do is we're going to do a calculation over the entire composition range of this, so across the different compositions of zinc. And so it's a similar calculation that we did before. We're assigning to a different name. You see earlier we assigned to this ref EQ. Here we're just going to assign to an object named EQ. And you'll notice we have a slightly different syntax here. So this syntax allows us to specify a range, like we're doing a step calculation. So here you can see we go start, stop, and then this is a step. And so we can now also run this. We'll do a Shift Enter. And so we've done our calculation also over this particular composition range. So now what we're going to do, and we're going to do a little bit more of a deep dive into exactly how to extract all the equilibrium results here in a little bit. But this is basically we're extracting the chemical potentials from the reference state, and we're extracting them also from the step calculation that we did as well. And this dot squeeze function, all that's doing is it's just flattening out the arrays, because again, PyCalphad has the ability to do multi-dimensional mapping. But in this case, this is a 1D calculation. So we just squash all the dimensions down into 1 dimension. And then we apply the thermodynamic definition of the activity here. And so we take the chemical potential difference relative to our reference state, and then we divide, we multiply, we do R times T. And now this ACR zinc contains our thermodynamic activity relative to the reference state. So now the next step is we just do a little bit of work in matplotlib to actually plot. And so we are including a scatter plot that has our experimental data. And so when we run this, we can see actually that the CalPhad prediction agrees pretty well with the experiment here, which isn't a surprise. Aluminum zinc's a pretty well-studied system, and the data definitely would have been available to the person who performed this assessment. So it's good to see that that intuition that we have about this being consistent is reproduced here. Okay, so any questions so far?
Richard, can I just ask, in the part where you were getting the chemical activity, there is a factor 8.315. I didn't get this one. Sorry, I was not listening carefully. Where does this come from? This
oh, sorry, that's R. This is the it's the ideal gas constant.
Oh yeah, sorry. Yeah.
Round it a little bit. Yes. Yes.
Thank you.
Sorry about that.
Thanks. Thanks.
We yes. Yes. Sorry. And to also answer another question about the units that PyCalphad uses. PyCalphad uses SI units everywhere as much as possible. So pressure is in pascals, temperature is in Kelvin, which sometimes comes up. The energy is in joules per mole of atoms that you get back from PyCalphad. So that's a note, but that's also documented on our website. So now we'll do something a little more interesting, which start thinking a little bit more about binary energy surfaces and the phase diagram. And so what we've got here is PyCalphad has the ability to compute energy surfaces for, well, for arbitrary multi-component systems, but in this case, binary is the easiest to visualize. So here we have a database from the niobium rhenium system, which was developed by Bashwan Liu and others. And so we have a little bit of work here, hopefully not too intimidating, but we have some work here basically to format this legend and get the nice coloring. But the core of this is the PyCalphad function calculate. So the way to remember this is calculate is for non-equilibrium properties and equilibrium is for equilibrium properties. And so what calculate will do is it will just randomly sample the energy functions in the database so that you can plot the energy. And so what we see here is so the energy functions as a function of rhenium content for all of the phases in the system. One of the ones you might be kind of interested in is this chi phase. You'll notice it's actually a multi-valued function, and that's because the chi phase has internal degrees of freedom. And so using PyCalphad, it's possible to visualize directly the energy of the internal degrees of freedom in a phase. And that is otherwise something that's not easy to do with other CalPhad-based modeling packages. And so we can just run that now, and you can see that we'll get the same calculation as before. And so now we'll go on to actually plotting the binary phase diagram. So we have a built-in function called binplot. And so we once again return to our aluminum zinc example from before. We can see we can produce this this nice phase diagram. So the signature for binplot is the same as for equilibrium, except what we now do is we have to specify a two-dimensional calculation. So we specify zinc with a start at 0, an end at 1, and a step of 0.02. And then for the temperature, we go from 300 to 1,000 Kelvin, and we step in 10 Kelvin. And then we have here, these are some arguments that just allow us to set the size of the phase diagram. So we can use, so this is a matplotlib function. And you can just configure the size of the diagram you wanted to have plotted out, and then it will plot onto that figure. And so you can use all the same matplotlib features that you may already be familiar with in order to customize the look of the phase diagrams. So we can also run it, and you can see. We also support, we do have the ability to for certain oxide systems, we can also compute the phase diagram. So in this case, this phase diagram only goes from 0 to 0.6 oxygen. I'm just pointing that out. The rest here is a single phase region, and I can just start that. It'll take a minute or two to actually do the computation because the ionic liquid is just slightly more complicated. And so we're able to compute this phase diagram as well. So I will pause for a moment. I'll queue up our next discussion, just in case we've got any questions we want to hit on.
Question about the list where we provide the list of phases actually here. And do you use the prior knowledge which phases are available already in the phase diagram, or for example, for aluminum zinc?
Which phases?
Yeah, here we provide liquid.
Yeah, so we don't have to do it. We can actually programmatically specify all of the phases. So let me show you, for example, the database object has all of the phases built into it. And so we can write, we can write this function which will give us all of the phases. So a common pattern that people will use is just give me all the phases, and you'll get exactly the same result from running it. So you can programmatically query the database and get the phases that you want as well. That's also possible.
Thanks.
So you don't have to know the phases in advance. But in general, we do recommend that you have some kind of familiarity with the database that you're loading, that you've checked to see what phases are in there. Some databases that are in the literature are not designed for all of the phases to be enabled at the same time. Sometimes phases are modeled with two different ways, and you're only supposed to use one phase or the other at a single time. So that's just little things you have to look out for if you're downloading a database you're not very familiar with. That's just something you have to check on. Thank you for the question. Was there anything else? So hearing none on this side, I think we'll just go on to our next example here, which is really more of documentation, and it's something that you can kind of read on your own, which is available to you. Although there are a couple of examples here, and so the way that PyCalphad returns results to you is in an object called an X-array dataset. And it's kind of like a pandas data frame, but it's designed for multi-dimensional data, not just tabular data. And so this notebook contains information about the dataset structure, and also with the variables that are used to define the return values. And so what we've got here is, so for example, inside of a calculate function, we have all these different coordinates here. So they represent the different dimensions of the calculation. And so in this case, we can actually access each component of the system, as well as all of the internal degrees of freedom. So these are called sometimes the site fractions or the Y fractions of the system. And then these are the coordinates, and then the actual data variables are the phase, so the name of the phase, the mole fraction represented at that particular data point, and then the internal degrees of freedom of that data point. And the output just represents the idea that it doesn't necessarily just have to be the energy that's output. It can actually be any property that can be computed out of that database. And so, for example, when we do a calculation and then we print the result, we can see here, we get a shortened representation of the data that's there. And so we have the ability to do lots of fancy sort of indexing into this result. So we can do things like index out a particular point, a particular degree of freedom, and a particular temperature, and actually get that value. And so you can convert this back to NumPy arrays and use it for any other follow-on analysis that you might be interested in. For equilibrium, it's actually fairly similar, but there's a couple of more options because this is can include multi-phase information, as well as the conditions that are involved in the thermodynamic optimization. So we have again these components and internal degrees of freedom. But now we can also specify the composition, the vertices. Excuse me, I should explain this. So the vertex doesn't have any inherent physical meaning, but it's kind of an analog to like the vertices on an equilibrium tile line. So you know, in a two-component fixed temperature pressure calculation, you may have two phases in coexistence at the same time. And so the vertex allows you to index either the first phase or the second phase. And then we also have some information here about the data variables. I'm not going to go into too much detail here in the interest of time, but a lot of the shortened names will be familiar to you if you've ever used thermocalc, for example. We have here the phase fraction, the chemical potentials, the mole fraction, the Y fraction of the results, as well as the energy. And then the output is basically whatever equilibrium property you specified at the beginning of the calculation. And so you can see here another example where we do this, this mapping calculation, and then, but now we specify output HM because we wanted to compute the enthalpy. And so we can run this computation and then get the results here, which will be contained inside of this HM attribute. You can also do sort of this indexing where if you want to return results where certain things are true. So for example, if you want to get all of the phase fractions where the phase is FCCA1 at a particular composition and temperature, then you can write this X-array indexing command, and you will get this result. And so what it does is it basically masks off all of the return values where your query is not true. So you just get the results where it's true. And so this can be a powerful way to actually control plotting or some other follow-on analysis you might be interested in. So I will, I'll just keep moving along here in the interest of time. Let's talk about custom models. This is one of the most powerful features of PyCalphad, and it is it really takes advantage of the modular nature of the package. And so custom models are a way to override the way that PyCalphad interprets the database to build the material property functions. And it'll become clearer what that actually means when we go through this example. So here we're going to take a CalPhad-based property model from the literature and use it to predict viscosity in aluminum, copper, zirconium liquids. And so I'm not going to go into the details and justify this particular model. You can go and read the paper if you're interested. But this is a class of, there's a lot of different types of viscosity models. This is a class of model called an entropy model. So it defines the binary alloy liquid under a small undercooling condition using the excess entropy. And so this is a great use case for PyCalphad because the excess entropy is something that's very difficult to measure experimentally, but it's very easy to calculate if you have a CalPhad-based thermodynamic model. So we're going to run our import line to once again import our database function. And what we're going to do is we take this existing aluminum, copper, zirconium thermodynamic database from Zhou et al. And we're going to add 3 new parameters to describe the viscosity in Pascal seconds of the pure elements, aluminum, copper, and zirconium. And so you can go and look in the aluminum, copper, zirconium database here, but we have already, you scroll down here, we've already added the parameters here. But in principle, you could have done it yourself. So here we go. So that's great. But if we try to load the database, you'll notice we get an error. We get a parse error, and it complains about this new database line we just added. And so why is that? So the reason is because this eta parameter type is not supported by default in PyCalphad because we don't know what that means. PyCalphad only knows what the built-in parameter types mean. So you have to tell the parser that eta should be on the list of supported types. And so we reach a little bit into the internals of PyCalphad now, which we're able to do because of the modular structure of it. And we basically append this eta as a supported parameter type. And now if we do that and repeat the command we did before, the database loads without an error. And so you can specify any parameter type that you might be interested in, and it becomes a supported, it becomes a parsable parameter type. Now, okay, so you can parse the database, but that doesn't mean it knows how to build the viscosity yet. We have to actually write the custom model. And so what we do is we have to write a new model class. And that model class is a subclass of the built-in PyCalphad model. And so here what we do is we override this build phase function. And what we do is we have to add a key line here, which is this line. And so we define a new property called viscosity, and we assign it to the model. And we set that to be equal to this function build viscosity. And so this is kind of the pseudocode version of this right here. But you'll see we haven't written the build viscosity function yet. The first step. So the build viscosity function has to do a couple of things. It needs to be able to query the database to get all of the eta parameters. It has to compute the weighted sum, which is again according to the model here. So we need to write down this model inside of the build viscosity function. And so we compute the weighted sum of the eta parameters. We compute the excess entropy of the liquid, and then we plug all the values in and return the result. And so that's what we do here. And so in the build viscosity function, we do add a safety check here because this model is only valid for the liquid phase. So we add a little check here to make sure that nobody's trying to calculate the viscosity of a non-liquid phase, because we don't know what that means in this model. So we do a little bit of work here. So we extract a phase object out of the database, and then here we're doing a little bit of functional programming. dbe.search. Search is a built-in database function which knows how to query the database. So here is our query for our parameters. So up here, this is step 1 here. So we write, where the phase name is equal to the current name of the phase, where the parameter type is equal to eta, and then the constituent array. So this is the list of either the pure end member or the interaction parameters. We use this built-in function called array validity, which will check to make sure that it only loads the parameters for the currently selected components of the database. So again, we're reaching in kind of deep into the nuts and bolts of CalPhad here, and that's going to enable us to actually build a new type of material property model. And in principle, you could be doing multiple parameter queries here, multiple types of things here, depending on the complexity of your model. And so we call this built-in Redlich-Kister sum function here to compute the sum here according to the Redlich-Kister formalism. In this case, we only define the end members. We don't use the interaction parameters in this model, though we could if we so chose. And then we define the excess energy. So we take self.gm. So GM is a built-in property for the molar Gibbs energy. And then we subtract away the reference energy. So that's the energy of the end members. And then we subtract away the ideal mixing entropy as well, or the ideal mixing contribution to the energy. And that gives us our excess energy. Then what we can do is we can then compute the excess entropy. So we just apply the thermodynamic relationship. So excess energy here, this is a symbolic expression here. And so we can actually use PyCalphad's built-in computer algebra capability and just write that the excess entropy is equal to the negative of the derivative of the excess energy with respect to temperature. And so we apply that, and then Ks is just a constant here. And then we're able to write down that the result is equal to eta, which is this weighted sum, times 1 minus Ks, which is a constant, times excess entropy divided by R. And this is precisely the entropy model that was written. And so we're able to write down more or less just the math of the equation and implement it within PyCalphad. And so now we have our new viscosity model. So now to put it together, we have to create an instance of this viscosity model to give to PyCalphad here, and then we repeat it again down here. So it's a little redundant. So we can call calculate to just compute the viscosity here of this material. And so in this case, the equilibrium and non-equilibrium mean the same thing because it's a single phase, single sublattice. And we pass into the key here is we specify this keyword argument model, and we put model equals mod. And so this tells PyCalphad to use not the built-in model, but our custom viscosity model that we just wrote. And then we plot it here to actually get, and so this gives us the viscosity of the copper zirconium liquid at 2100 Kelvin. And here we multiplied times 1,000 to write it in the more standard units of millipascal seconds. And so this gives us the temperature dependent viscosity here. And then we just repeat and do the exact same calculation for aluminum copper at 1300 Kelvin. And we could do this calculation also for copper, aluminum, zirconium. It's just a little harder to visualize. So this is a whirlwind introduction to what I consider one of PyCalphad's most powerful features, which is the ability to define custom property models. So are there questions about this? Okay. Well, so if you do have questions or follow-ups about this, you have our contact information and our Gitter chat channel. We're happy to work with you on this for anything that you've seen so far.
One question. Sorry.
So I did. Go ahead.
For the build viscosity function that you wrote, you said we do a check to see that we are only checking for viscosity of a solid phase. How could you go over how exactly you did that check? I'm sorry, I missed that.
Sorry, we only do the viscosity for the liquid phase. So this line right here is what does it. So model has a built-in property called phase name. So all models know their own names, so they know what phase they're defined for. And so we just do a check when we call build viscosity, and we just make sure that the phase name is liquid.
Okay.
So yeah, we're trying to save the user some trouble so that they don't accidentally use a viscosity. They try to write down and apply this model for a solid phase, because this model is not valid for solid phases according to the literature paper. But you could define a material property model for a solid phase just as easily. It just depends on whether it's physically meaningful or not. Other questions?
Just short question. If one is interested in calculating the viscosity for polymers, does the structure of PyCalphad allows to calculate that? I mean, apart from the databases, which we would need that.
Yeah, so it's absolutely possible. There's a lot of interest, I think, in the community for making CalPhad more applicable to polymers. You're right that there's not really a lot of databases you can find in the literature currently. In principle, it's absolutely possible to apply PyCalphad to polymers. You will be building your own databases for that. And you will probably also have to do a little bit of work writing your own models as well. But the only real constraint in the types of models you can write down are whether you can kind of fit it within the existing compound energy formalism. So if you can express things in terms of, or somehow map it onto sublattices or site fractions, and even that constraint can be relaxed under certain circumstances. So there's a lot of flexibility that's available. But you should be aware that that is I would say today is kind of a more advanced use case, and you have to be prepared to do a bit of work and probably a bit of your own Python programming to support that.
Thank you.
Yep. So I did want to take an opportunity to show you guys our multi-component capability. So this is, you've already seen this calculation or this type of calculation from the other results, but we often get asked about whether PyCalphad is useful for multi-component or not. And I just want to show you here that it is. And so we have this database. This is an open database from MatCalc, which has been modified to work with PyCalphad. And so we get some warnings at the beginning, and that's just because this database was designed to work with MatCalc and not with PyCalphad. And so it just provides us some warnings to tell us that there's some inconsistencies, but we are, in this case, safe to ignore that warning. And so here, we do a little bit of work to set up our equilibrium calculation. So I'm going to start it running because it's going to take a couple of minutes to run. I'm just going to talk you through it. And so this is a calculation that we're going to do for kind of an analog to stainless steel 316. So the full multi-component system is listed here. And PyCalphad can do the computation, but unfortunately with the computational resources that we allocated onto MGF Cloud today, the most number of components we can run is about 6. So I set up a 6-component system here to run this, but you can definitely do the full multi-component as well. I want to also explain this phases line we did here. So we do a little bit of something fancy here. So we once again call this dbf.phases.keys function. So this gives us a list of all the databases, of all the phases in the database. But what we want to do is we want to say, I want to do all the phases in the database except one. So in this case, this GPMat phase is only for if you're doing precipitation simulations. And so you can suspend it. So we use this Python set notation to subtract it out from the set of stable phases, and then we call a list to convert the set back into a list. And so it's a little bit of Python container stuff happening here, but it's just a shortcut for us to get a list of all the phases that we want, because again, there's quite a number of phases in this database, and so to have to write them all down by hand is kind of a hassle. Then we have here, we're showing another feature where we can write down things in terms of mass percent. So W is the mass fraction, so we just write the mass percent divided by 100, and that gives us the mass fractions. And then we have to write, we use this get mole fractions function to convert everything into the mole fractions that we need for our steel calculation. And the rest is just the standard PyCalphad stuff you've seen before. So we're writing down the conditions. We're getting the start temperature, the finish temperature, and then the step size, pressure, and the total size of the system. We also have the ability to control some of the advanced options for how the calculation is performed. And so in this case, you don't normally have to pass an option like this, but I did this. I decreased the point density a little bit to make it fit within the memory requirements here on the cloud system. So it's just a little bit of a constraint we have to work inside this cloud environment, but it's not an inherent constraint to the PyCalphad package. So it's still taking a bit of time to run here. And so I'll just keep talking in the interest of time, and we'll check to see when this is actually ready. So once the result is complete, we have the ability to look at the phase fractions versus temperature and to plot the different phases here. And so we can see some of the results here may not necessarily be consistent with what you'd expect for steel all the way. You would expect FCC to be stable all the way, but that's because we removed some of the components in the calculation in order to support this. And so we've got now the phase. Sorry, a little bit of noise outside. We have now this for loop, which will plot each of the phase fractions versus temperature. There's a little bit of indexing magic happening here. But one thing I'll explain is that this phase indices 2, so the number 2 comes from which dimension we get from the output of this. And so it goes in the order of NPT. And so T is the third element of this index array. And so we use 2 because Python objects start indexing at 0. So that's just a little bit of magic that we have to do there in order to make this work. And so it's just something that we're doing to manipulate the result of the calculation to get the result that we want. Oh, and our calculation finished. So we can rerun this and we can see that we get the same result. We also have the ability to extract the individual compositions of the phases. So down here, we plot just for the sigma phase. And we do the same thing that we did above, except now we're just extracting the mole fractions of the components. And so we run that, and then we can also see, and so you might notice it's cut off. It doesn't go all the way up. That's because this only returned the compositions where the sigma phase was stable. And so we don't have a result for any metastable values here. But it is possible to do that computation, but we would have to do it as a separate step. And then we repeat the same thing for the FCC phase, which is stable in the entire region. And so you can see how the compositions change with temperature over time. You also notice we did a unit conversion down here for Celsius. There's no magic there. We just we subtracted 273.15 from the results here, which were in Kelvin, and that gives us everything in nice nicer units than depending on the audience that you're showing the results to. So that's the result for multi-component. Any questions? Hearing none. So we'll go to our last intro, or our last exercise here, which gets into a little bit with reference states. So by default, the energies that are calculated are, in a sense, absolute energies that are defined in the database, and they're not guaranteed to be with respect to any particular reference state. But we are able to leverage our PyCalphad model objects to define arbitrary reference states using our shift reference state command, and then compute these new properties for the energies that are relative to that reference state. And then those properties they get the suffix R, where it's the molar Gibbs energy with respect to our reference state, or enthalpy with respect to our reference state. And so we have an example here of the enthalpy of mixing of the liquid. So once again, we return to our niobium rhenium system here. So we're putting a lot of pieces together now. We're adding additional import lines for our reference state object inside of PyCalphad, where we're computing, generating reference states. So in this case, we're defining a reference state relative to the liquid. And that's because we're going to compute mixing in the liquid. And so we need our reference states of the liquid. So we create a model object. So that's just like what we did earlier, where we created a custom model object. But in this case, we're using the built-in model. And then we're just calling our shift reference state function, which it just accepts these two arguments. So I'll just run it. It accepts these arguments here, and you can read the details about it. The database are the main things you have to specify. There's also some advanced options to control exactly which energetic contributions are used to define the reference state. But in this case, we just use the defaults. And then we put this object into a dictionary and then pass it over to the calculate function. We could also just pass the model object directly. That would work as well. or you can put it inside of this dictionary and then put the name of the phase and then the corresponding model object. Either one is possible. And so we scroll down and we can see now that we have the mixing enthalpy. So we computed the enthalpy with respect to this reference state. And so this reference state is the liquid. So of course, when you subtract there, you get 0 and 0. So that's exactly the mixing enthalpy. And so you can do this for any property that you can calculate with PyCalphad. So sometimes you'll see enthalpies of formation used to define a convex hull in the literature. You'll also sometimes see this for data that's been reported in the atomistic community. And so PyCalphad has the ability to compute convex hulls with respect to those reference states as well. And so we have here, we're defining new reference states. Now we're defining niobium with respect to BCC and rhenium with respect to HCP. Some of you may recognize that this is precisely the standard element reference, the SER reference state that we're defining here. And so we go down here and we write a for loop now to save us some trouble doing what we did before. So this will just call the same thing that we did before, but for both of these phases. And now we go down and we compute the reference enthalpy, the enthalpy at our reference state using the desired settings. And then we do some very nice matplotlib magic. And again, this was primarily written. I do want to thank and acknowledge Brandon Buckland, who did a lot of the work to put this example together and produce this nice visualization, which we can now run and see that we can compute the enthalpy of formation. And then it's even nicely color coded so that we can see the coexistence regions of the different phases. So of course we recognize these kinks in the curve corresponding to phase transitions. So it's exactly what we would expect. We do also have some special built-in reference states for mixing. So you don't necessarily have to do all the work to set up mixing if you're particularly interested in that. We have it built in using this mix suffix. And so if we just specify HM mix, then you see we can also compute the mixing enthalpy. But the cool thing is we get not just the stable enthalpy, but we get all this nice metastable mixing enthalpies as well from the internal degrees of freedom in the chi phase. We also, I don't want to take too much longer, we're almost out of time. We also have the ability to compute specific site fractions. So if you're interested in exploring particular internal degrees of freedom, we also have the ability to do that calculation. The experience isn't quite as nice. You do have to put the NumPy array together yourself for the site fractions, but you're able to take the site fractions array and pass it directly to PyCalphad to compute. So you can use PyCalphad as your own Gibbs energy function calculator and specify the site fractions directly if you would like. So we covered a lot of stuff here, but this is the end of the PyCalphad material. So do we have any other questions or things we'd like to hit on?
Hi, Richard. I have actually not really a question, but it's more of a comment. So yeah, great work and explanation. And I've been following actually PyCalphad for a few years on GitHub. And actually just one small little thing that I could not pick is, which is in the bin-plot function, you pass the quarks arguments to the matplotlib plot functions as a separate argument. Any particular reason why you don't like pass these quarks directly to the bin-plot function and you separate them?
So,
yeah,
so you're talking specifically about this trick.
This is something that really yeah, bothered me actually for a few for a few years. Instead, you could first.
So the reason we do this is it's a separation of concerns issue. So binplot has the ability, and Actually, we did a few versions ago, exactly as you said, where you could directly pass the keyword arguments, but we changed it. The reason being now that binplot has the ability to pass in these plot keyword arguments, but you also have the keyword arguments to control the mapping and the equilibrium calculation. And we wanted to guarantee that there was no chance that those keyword arguments could ever collide.
Yeah, I see.
So there was just an approach to separate the equilibrium keyword arguments and the plot keyword arguments. So that's why we did it.
Yeah, I understand. Yeah, thank you.
Yes. I apologize for the frustration it may have caused, but we did it for a good reason, if that makes you feel better.
Yeah, of course.
So one thing, just in case you guys forgotten or don't know, you can right-click on the workshop folder here and click download as an archive, and you will save everything you've done to your local computer as a zip file. So that's an easy way to take everything home at the conclusion of today, just so you are aware of that. All right. Well, thank you guys. And thank you for bearing with me during some of the unexpected interruptions. It's always, that's the rule with live demos, I think. Okay. Well, that's all I have up to this point. So I think at this point, we're going to transition to the next speaker, who is Brandon Buckland, who is the lead developer of SBay. And he's going to walk us through kind of the continuation of the work that we did yesterday, which was in the atomistic calculations and showing how to generate the free energy functions using atomistic simulation. And now we're going to learn a bit about how you can then take that data and further refine it to achieve accuracy and agreement with experimental data. So Brandon,